All right, everyone, thank you for inviting me. So I'm going to be talking about geophysics and amateur radio. So my background is I'm a geologist, and I've been doing some work with ham radio and geology, and I found where it came together is geophysics. In particular with ground penetrating radar, hence my call sign W0GPR is in honor of that. And what we're looking at here is actually a GPR profile that I took up in New York State, and this is looking at some interesting glacial stuff. So this talk is going to be focused for people who are interested in kind of how the ground affects it. There'll be some technical stuff, but I try to keep it down to a minimum. So it's tying in what we know about antennas, antenna systems, and then bringing that together with what geology is, and then finishing up with some geophysics. So basically, variability of the ground, this is what geology is. It's not some nice layer cake, although that's what we see in Kansas most of the time. Basically, how the ground itself affects our signals, so some of the properties that go into the ground that we can measure. We always hear about, okay, average Earth, perfect Earth, when we do antenna modeling. What do those mean? What are the numbers that go into it? And then thinking about what physically is happening in the ground and how things can change. And then where I come in is geophysics, and that's how we see it. So basically, the ground is very variable. This is what geologists study all the time. We look at structural geology. This is how it changes. Lithology, as we call it, or basically it's rocks and dirt. We have rocks versus sediments. Rocks is dirt that has just been heavily compressed. Either that or cemented together. And with that, there's something of the rate of change, so how quickly it'll change from one thing to another. Water is a big influence, as we'll see with the impedances. Also looking at the chemistry. Chemistry is very important, and that is important because it then goes into some of the properties that we look at. So in particular, structure, as we can see here from Kansas, this is very flat, and we have a lot of different rock types here. We have some shales, which is this really stuff that powders away nicely, as well as some limestones. And so all these have different radio properties that our antennas see. And this is what gives us our ground system. And so part of that's understanding it. Next, we can see how we went from that nice layer cake into a lot of faulting. So this is actually out in Moab, down in Utah, just outside of Arches. And this is an area where basically you have all these faults. And so what I'm trying to convey with this is you could have your antenna at one spot, but what you think is underneath of your antenna, maybe 5 feet over, is drastically different. What does that mean? Well, most of the time not much, but if you're trying to do modeling, maybe understanding what your ground is on could be important. We also see that some nice folding. This is an example up in Bennington. You can see that the land surface above it is very flat, but when they cut in the hill to do this bypass, there's a lot of folding in that limestone. And this is something that limestone we see here in Kansas a lot. There's something called caves or karst features. And basically that's where the limestone's been eroded away. So you might think that you're putting into a good strong bedrock for your tower, but if you were to go down any farther, you might actually hit a sinkhole. And that's something that we see. We're seeing the same thing in different parts of Kansas, where in particular in the Hutchinson area where they have a lot of salt, that salt is basically it is weathered away. So the water in the ground dissolves that salt, you have a big hole, and the ground sinks. And so these are some of the problems that could occur with antenna sites. And so it could be close to the ground or it could be fairly deep. The other thing is the ground itself can be very variable. This is looking at sediment itself, and this can be very important. So the idea is we have clays in green. Clays are very good. We have a lot of those in Lawrence, Kansas. They're very conductive, which makes for great grounds. And then we have sands, and these can be deposited by rivers. So very similar, we could be on the banks of the Kansas River here, or in the flow channel of the Kansas River, but off to the sides we have a lot of clay. So if you put your antenna here versus here, even though there's clay on the surface, if you go down a few feet, you might be above sand. And so when you think you might have great results, you might actually have really poor results, and I'll get into that in a little bit. So with this, the geology, the stuff that we're building on, can be very different in a very short amount of time, a short amount of space. So it's very discontinuous. So basically what this comes into is some of the ground variables. Chemistry is important, so water can have a huge effect. So if it's been dry like the last couple of days, or before the last couple of days, and all of a sudden gets wet. If that water is wet all the time versus if it's dry or wet. So you might find that your antenna system works really, really well after a rainstorm. But if it's been dry for a long time, your antenna system, the quality might change. And so if you're trying to do accurate measurements of your antenna's directivity, it could be changing due to something as simple as the ground moisture. Do we experience it? We don't always know, but if you're interested in a lot of precision and trying to find some rare DX, this could be something to think about if you're so inclined. So some of the things we think about is conductivity, which analog for that is a resistor. We have magnetic permeability, and that's inductance, or dielectric constant or permittivity, and that's capacitance. So these are all things that we see in the Earth in geophysics. And so if we think about the soil, we can think of it as a lossy capacitor. Different types of soil will have different electrical resistance and different types of capacitance involved. And these are all things that your antenna sees when it creates, when you transmit. So here's a look at the United States. A lot of the figures I have are from the ARRL's antenna handbook, so these are something that you can go and look at and do comparisons. This is a look at the conductivity map of the United States. Actually, some of the highest is right here in Kansas, where we're at 30. If you want to look at some of the lowest, you can go back to my house in Pennsylvania and 2. And so things can change over a wide area. But this is more for broadcast. It could be, as I was saying before, it could be changing between the size of this room. We could have high conductivity over here and low conductivity over here. And so part of that is understanding your ground system, and it can be very variable. And if anyone has questions or any topics they want to bring up as I'm going, please let me know, raise your hand, and I can answer anything, because I know that a lot of people might not have much experience with geology, and it's definitely a foreign language like ham radio is to a lot of other people.
What dimensions are you using when you say you have 30?
That is in millisiemens per meter, so that's the conductivity. Salt water, they say here, is 500. When it comes to the actual dimensions, I'm pretty sure it's in millisiemens. Those numbers I've seen as high as 300 millisiemens, or as low as lower than a millisiemen. So for example, quartz is very low conductivity, clays can have very high, salt water is 5 Siemens. So a Siemen is, or sorry, conductivity is resistance that you divide resistance by 1. So it's 1 over the resistance you have conductivity. So going back to when you took the test. So does that answer your question? Okay. So the next thing to think about is, so now we have seen how the geology can change. How does that affect our radio signal? And some of those things come to with skin depth. So basically, how deep is our radio signal penetrating into the ground? That will change on the frequency. It will also change with the power and the ground type. We have the near field versus far field effects, the frequency dependence, as I mentioned, and as well as the antenna coupling. So we've seen this when we raise our dipoles higher and lower, this will change the effects on the antenna. So what's actually going on? So basically, skin depth is the idea of attenuation, loss. Same thing with coax, only a lot lossier. We put a signal into the ground, and as it goes deeper and deeper, it decays. And so this gives you how deep of an effect do you have. If you're putting up a ground system for a vertical, this will help you determine how many radials you put in the ground. The more is better, as you say, but there's a point where you can put in so many, you don't see much of a gain for that, and the ground can help you in understanding how good of or poor of a ground you have. So looking at skin depth, this is basically how deep your signal is going into the ground. For example, seawater, as everyone says, is fantastic. It's really highly conductive, and it has a lot of capacitance. So it's basically a gigantic infinite metal sheet, and that's why it works so well for boats for multiple purposes. So this is a look at frequency. This is at 100 hertz down to 160 would be right about here. And then how deep into the soil this goes. This is in meters, but you can think of it in yards. So as we can see with seawater, it doesn't go that deep. It might go in a yard all the way down at 100 kilohertz. And so how do we talk to submarines? Brings up that question. As we can see, we don't have much going into the water, which is great because that means that all of the energy that we are transmitting is not being lost in the seawater. As we go up into poorer and poorer soils, for example, highly sandy soil that's very low conductivity, we can see a lot of our signal that we transmit out is going into that soil. So that signal that we're not putting into the air. And so sandy soil is not very good. The other thing is, looking at the dependence on frequency, this is a look at different conductivities. So the upper conductivity, these four, is 10 times less the amount of conductivity that's in these ones. And what we're seeing is, from that map of the United States, the conductivity has more of a role than what we see as in our HF bands. We see more of the dependence on what are the soil conditions, if it's sand and clay versus just what's the electrical conductivity of the soil. So now we can think about the soil itself. There's thinking in the near field versus the far field. So the near field is when we transmit. The antenna itself is putting up energy around it and the things that are in it. So if I'm standing next to my antenna, if somebody else is standing next to my antenna, there's a tree in the way, all of these things affect the antenna system. And so part of that is understanding what is affecting our antenna system. In a vertical, that's why we put up a large number of radials, is to prevent the ground immediately near it from affecting that system, and it radiates out a lot of it. So right when the antenna is being fed, there's a lot more effect than say a quarter wavelength away. So if you're trying to make an effective ground radial system for your vertical, understanding the near field is important, what's involved. So if you're compromised in a city lot and you have radials that are coming out and making room for a building, well, what will happen is your radiation pattern will be skewed by that. So your initial thought of a nice donut shape of radiation away from your vertical, the presence of that building will change that and might give you results different than what you're originally thinking of when you built that antenna. The next is the far field. So once we get away from the antenna, this is what makes when Jim talks to Bill, this is what makes his signal be different. So you have the ideal idea of what your antenna's radiation pattern is, but that far field basically is reflections. And so you have this great donut, but your low angle reflection gets diminished. Well, what happens is in the far field, or as it goes away, you have an initial transmission, or you have the direct wave, but then you also have a reflected wave. And the change, the timing of this, the difference of that gives you either a strengthening or weakening of your signal. And this point here, when the energy reflects off of the ground, if it is seawater versus sand, that can have a big effect. That's why if you have a vertical on seawater versus a vertical on sand or near sand, what will happen is that energy enters the sand. It doesn't reflect perfectly. This is something that we see in geophysics. It doesn't reflect, and there is a shift of the timing of that signal, or phase shift. And so that basically prevents you from getting nice low-angle radiation. That's why seawater is so good for low-angle radiation off of vertical. And so we can see there's some more stuff that goes involved with that, but that's... so switching from a vertical to a horizontal, this is a comparison of a horizontal dipole at a quarter wavelength versus a half wavelength. This is something we'll always see, is what the radiation pattern looks like above the ground. And as we go above from a quarter wavelength to a half wavelength, we see the difference, the change in the ideal radiation. We see, so this is in free space, is the dashed line, looking at the dipole on end, and then looking at the dipole on the side. we can see that we actually get more energy. Well, that's because of the reflection in the far field. And same thing with this, away from the ideal free space antenna. Well, what we don't actually think about in ham radio is what is the energy doing when it's into the ground. So we actually lose a lot of energy into the ground, and that's seen as we go closer and closer to the ground. The idea of NVIS antennas, we're losing a lot of that energy into the ground, but it gives us nice uniform coverage that gives us the vertical incident skywave. What we actually see, and this is something from GPR, is what I like to call the sugar plum fairies from Fantasia, because this looks like them. But this is what this is the energy that you're putting into the ground, and we can see that a good deal of it, in some cases, the majority of the energy is just being lost to heating the sand, killing worms, and so. It's kind of another perspective of that 100 watts of energy. Well, all of a sudden 50 of that just goes into killing worms. It's great for if you want to talk through caves, and people have actually been doing 80-meter Morse code, I believe, into caves through putting the antennas on the ground, but at other angles. So, any questions?
Well,
Yes.
What if you poured a concrete slab and put your antenna in the middle?
Like put it into the concrete?
Mount it like a tower.
You got a concrete slab
Mhm.
underneath it, say,
Mhm.
I don't know how big, but your antenna's in the middle of that. Isn't that gonna keep it from going in the ground?
Concrete is actually a very good, let me put it this way, it's a very clear substance. Now if you had like rebar and stuff, that will give reflections, but concrete is very clear to radio frequencies. So you'll lose a lot of energy into the concrete. If you were to just put it on the concrete. Concrete is not very
That's not
reflective.
gonna help.
So if you wanted to, you could put out a screen into the concrete,
Okay.
but it's not going, the concrete itself, and actually what's considered the worst is asphalt and concrete for what's considered a good ground for ham radio.
Yeah, I started with 10 radios, I added another 10, then I added another 10. We currently have 30 radios on the vertical, and they are random lengths between 40 meters and a quarter wave, but 40 meters and 20 meters. And pretty much around, except for it's close to the house where I had to bend it slightly, but I didn't see much difference. And once I had that number of radios, it worked pretty well. The pattern, it's a guess, but you hear stations, based on conditions, and it's pretty reasonable launch and very little straight up. So it worked pretty well.
Yeah.
There are 30
Also-
radios with number stranded 22 on each radio, so it costs money to put all those radios in.
Also, your noise went away, pretty much.
That was for other reasons, but yeah, pretty much, yeah.
They had a big effect on his noise.
Some of the modeling I've seen, and this is also in the antenna handbook, is it's in some ways it's better to have a lot of radials that are short rather than a few radials that are long. And it's all because of that near field effect. So there's a lot more energy. So if you think of a dipole, you have a lot of current at the feed point in the center of the dipole versus the currents where you get a lot more of the field set up. And so in close towards the feed point, you have a lot more of an effect. So if you have radials that are closer spaced or smaller angles, you have less loss at that high current point into the ground. And so there's what you can do, you can chart basically how long your radials are versus how many radials you have. And if you have, say, so many lengths of this length of wire that you can work with, how can you optimize your radial system for numbers versus length? So that's part of it. Yes?
Brandon, I have a vertical, but I have it mounted 21 feet. The base of that vertical is 21 feet above the ground. And I only have, because of my space where I live, I only have 2 radials for each band. There's 4 bands in that antenna. And so I have a quarter wavelength for each band, 2 radials for each one, and they're coming down at about a 45-degree angle, and they do not go into the ground, and it is not grounded. So what's the situation there?
So because you're not actually on the ground, even getting the antenna, the vertical off the ground by 4 feet, they're showing that it can help a lot. because you don't, the ground is, the air between the ground, you don't have the losses. And so air, like air capacitors are great because the breakdown voltage is relatively high compared to something else. And so you don't have loss in resistance, and it allows you to go for fewer verticals. But what they're seeing is the vertical, or where the radials are spaced, if they're spaced off, if they're not perfectly oriented, then you can have a lot more of effect. So being off the ground is a lot better. You can get away with four radials, 4 feet off the ground is equivalent to 32 radials on the ground for losses and for your low angle, your near field effects. But it's more finicky for how those radials are attached. If one's drooping more than the other, if one's off rather than being at 180, it's kind of skewed. And so by having it off the ground, it can be a little bit more tricky to get it perfect. So this is a look at basically, as we've probably all seen this before studying for tech, but this is a look at, this wavy line is for a horizontal dipole, this is for vertical, and for vertical dipole rather than a vertical ground plane, and this is the center of where that vertical is being fed. So as we bring the horizontal dipole away from the ground, for basically salt water we have this, for lossy ground we have this, and this is because of that loss of the energy into the ground that I was talking about. For a vertical, however, it does not change much because of the antenna polarization. And we can see that there's approximately around, what is it, 0.375 wavelengths. We go to a peak and we go back down. This is where, as we go up, we change our pattern and we change the timing of the reflections from the ground directly underneath the antenna to where it gets to the center feed point, and that'll give us changes in the impedance. And this will be different based on what the ground is. So any questions with this? So looking at some different comparisons, this is a look at perfect seawater versus average ground. One of the great things about seawater is we have, as I was mentioning before, those far offset angles. We have doubling of our energy. This is because of the signal from the actual transmitted antenna, the direct wave as well as a reflected wave off the ground, it reinforces. Whereas when it comes off of the imperfect ground itself, we can see where there's a loss of energy at these lower angles. Doing a comparison of a horizontal and a vertical in poor ground, and then a horizontal and a vertical on seawater. So this is how we can see that there's effects of the radiation pattern just based off of what the soil conditions are, what we're working with.
How deep does the water have to be so that you can really get the effect, and with the salt?
It's the skin depth. So off of that graph that we saw before, with salt water, it could literally be probably 3 foot deep. So if you want to make a reflecting pool of salt water, that'd be great.
I'm just thinking, my wife wants a lily pad and saltwater flowers, and I'm ready to go.
There you go. What's interesting about parts of Kansas is this many years ago, a little bit more than we've all been around, probably even together, this used to be a seaway. And so that's what gives us the Hutchinson salt mines, is there are layers of salt. And as I was saying before, that salt is being, as water runs through it, it dissolves the salt. And in some areas, that salt water can be within reach of a water well. So if you go out in some parts of the state, drill a water well, at 40 feet you have salt. And that might be an effect on your antenna. In parts of New York, they have similar effects where they have salt water and they have natural salt springs coming up. So unfortunately, it's a wildlife protected area because it's a sensitive ecosystem, but a great place to put an antenna.
Have you been in the salt mines?
I have not. That's on my to-do list.
That's a to-do list, yeah.
Yeah. So we all ask ourselves, how do we get perfect ground? What do these numbers mean? And what is average? So air, just for an example, we're looking at some different properties. This is the squiggly E. This is our permittivity, or basically our capacitance. This is a relative number. Arrow, as we can see, is basically 1. If you want to see the actual numbers, I have those on the side. This whistle-looking thing, or sigma, that is our conductivity. So basically, that's our wire. And then this weird-looking U, or mu, that is our magnetic permeability. So if we had iron in our soil, that would also have an effect. We can see that air is pretty low. That's kind of a good standard of 1. If we look at our impedances with that, that's the magic 377 ohms of the impedance of air. Our average soil has a number of 13. That's about a good sandy clay sand soil, like what we have here in Lawrence. In fact, we're a little bit above average. And then perfect is seawater. Water, as we can see, has a very, very high capacitance. And so normally with soils and sediments, we have between, say, 4 and 20. Water has a huge effect. This is why when it rains, all of a sudden that capacitance that around your antenna can change, because the water has such a huge effect, which is great for geophysics as well. Also, it's the salt water versus regular water. Regular water doesn't have that salt content, so if you're on say one of the Great Lakes, you'll theoretically have different qualities of signal versus if you're on the sea or
We all need
Salt Lake.
to move to Salt Lake City.
Exactly. So basically, looking on a scale of where Lawrence is, we're doing pretty well here in Lawrence. We have very good clayey soils, which is, to my bugaboo, horrible for GPR. So a quick look at geophysics. This is will be fairly quick. Some of the ways that we measure this stuff is through ground penetrating radar. This is a system where you have a transmit antenna and a receive antenna. This is in the HF and the VHF up to about 1 gigahertz. And the other thing we do, so with that, is you send out a quick pulse. It's a very short wideband pulse that hits things. Same idea as how we look at coax. You can send a pulse down a coax. Whenever there is a change in the impedance of the coax, we get a reflection. We see this with mismatch in our antennas. Wherever there is a change of impedance, we get reflected energy back. And we're using that same principle by measuring the ground. We send out that pulse, and whenever there is a change in impedance, going from one layer to another, we get energy coming back to our receive antenna. And so that's how we can see the Earth.
Was that like sonar?
Yep. It's the same idea as radar or sonar. It's just instead of sound or going through the air, we're dealing with different media in the Earth. So it doesn't go as far, and the resolution is much, much lower. The other thing is electrical resistivity. By measuring the resistance of the Earth at different points and at different depths, we can make a map of contaminants, salt, different types of soils, and we can use this to do engineering practices. So this is what it looks like. I'm the one taking the picture, so you can't see me. But
Can you find oil?
not with this. The oil's way, way too deep. And also, in a lot of areas, you might not be able to get through some different layers. The same ideas apply with seismic, which is what I'm actually doing my research on. So this is two 100 megahertz antennas. You see the guys pulling the sled, and this survey line is actually the first one we saw. And in here there's gravels, there's till, there's clay, and this was all in a glaciated zone where a glacier slammed up and moved everything around. So we were trying to map it. And the gentleman we were doing this for was going to decide to go from farming to gravel mining based off of some of the stuff we found. So, great. So, this is some of the things we could look at. Like I said, water comes up very nicely. Well, there's the water table. That's why they stopped mining it there at the old pit, because they hit the water table, get a really nice strong reflection. And we can see this is basically that first shot of energy at the top. And we can see here's probably a power line that's reflecting down and some other stuff going through. So these are some of the images that I look at and strain my eyes at every day. Next, this was one that they did for looking at a tunnel. We have diffractions from tunnels, and then these are drain pipes. And so these are ways you can look at large-scale features, and this is with 50 megahertz. Yes?
I just had a strange thought. when you have spare time, which you don't have as a student, go over and look at big data.
Mhm.
Big data may have some application to this field unless you're already doing that.
We'll talk later.
Yeah.
Okay. So, kind of, once again, getting back to the idea that the Earth that we're transmitting on can change very rapidly. We have sediment here, which is great for antennas, but horrible for GPR. That's why it's clear, because there's a lot of loss in there. Some of you might be thinking, well, then how, if we lose all this energy up here, how can we see down here? Well, that's because we multiply it and well, we make it bigger. But here is sand, so you might think you have some really good soil, but as you go down, you might have some a larger area of poor soil. The other idea that this is something you can actually go do with a car battery or 9-volt battery and your ohm meter and some 4 barbecue skewers, is you can measure the resistance of your lawn in different parts. And so this is a way that you can, with these 4, some different setups. If you're interested in looking into this, we can talk later. But by measuring the voltage and the current, you can measure the resistance at a point. You move that thing along, and you get different points. As you change the spacing and different parameters, you can go and down deeper. So when we take all those points, we can make a map, and we can see down to the Earth the electrical resistivity. So this is in ohm meters. We can see clay, we can see bedrock. You can use this to see faults, different things like that. And so I've used this in areas where I was talking about in New York, of mapping some of these salt features and some of the dissolved salts going through channels, and also with contaminants. And so for hams, this is a way that you could, with the simple tools I mentioned, you can go out and you can measure the properties of your property.
Is that what you're doing at Don Morris's house?
Oh no, I was shooting guns in the ground and measuring the energy coming back. So same idea as GPR. The gun gives a nice pulse, and then wherever it hits a reflection, it comes back up. I have receivers, and they're basically glorified microphones, and I can listen to, or they detect the ground motion, and so then I can make maps of it.
So how the heck do you wind up finding out the ideal place to put your antenna?
Well, the first place is you put it up and you go from there. But this was for some things to think about if you have a large plot of land, something if you're interested in doing a survey. When it comes to amateur use, please don't let this prevent you from putting up an antenna. It's better to have some wire than no wire. And but I guess for those who are really interested in doing some modeling or thinking of how can they take, for the fun of figuring out an antenna system, take it to the next level, this is where you can do it. There's not much you can do to change your ground. Based off of the idea of skin depth, for HF, you're not going to do much. For VHF, if you have sheet metal, you could put something on your roof to make it a little bit better. But once again, these are things that are out of our control. If you're so inclined to figure it out, these are things that you can measure, and there's some different ways to do that out there. But I just think it's kind of fun, and what's interesting is the difference. What makes it great for GPR makes it horrible for ham radio, and vice versa. And so this was kind of a nice place where my ham radio background and my geology background and my previous job came together, and that's why I'm doing what I'm doing and why I'm here. So I like it. It's fun. It's I mean, it can get a lot more esoteric and complicated than that, and if you're interested in some of those finer details or some of the stuff I've done, just let me know. So, I've got some extra slides if people are so inclined, but I think we've all suffered through enough.
Now you got me
Too much
wondering if
technical.
I should put radials on my 2-meter.
The J-pole you have, the way it's designed, the nice thing about J-pole, it doesn't need radials. So we'll leave it at that. Any questions?
Yeah, you just had me wondering.
Well, thank you very much.
I'm gonna put radials.